So in this video we begin organic chemistry content that is post the AS qualification, and the first one that we're going to look at is, or first part of organic chemistry that we're going to look at is the final type of isomerism that we have to study in A-level chemistry. So let's just briefly remind ourselves of what it is that we have covered, and also the sort of the gap that we've still got. So right at the start of the organic chemistry, the stuff that we did in year 12 in the introduction to organic chemistry, we looked at isomers, and we initially looked at structural isomerism. So in structural isomerism, and this is true of all isomers as well, we're looking at molecules that have the same molecular formula, right? So that means they have the same number of carbons or of hydrogens, of oxygens, etc., etc. In structural formula, the difference between different isomers is that they have the way those atoms are stuck together is different. So they have different structural formulae. Okay. And we can break down the types of structural isomers into three. So we can look at, we looked at functional group isomerism, and that's where, again, always have the same molecular formula, but this time they had different functional groups. So they tended to come in pairs. So a single carbon double bonded alkene could have the same molecular formula as a cycloalkane. So they had the same molecular formula, but they had different structures, and we could identify which was which if we knew that one was one and one was the other through the use of bromine water. So bromine water would decolorize with the alkene, but it wouldn't with the cycloalkane. We looked at position isomerism. So here they have the same functional group, so they may say all be alcohols, or they may all be haloalkanes. But the position of that functional group differs. So it could have been one chloropropane or two chloropropane. So they would have been position isomers of each other. And then finally, or perhaps the one that maybe we looked at first, was chain isomerism. So here we were comparing, it was really about branching, whether there was branching or to what extent there was branching. So a very simple example would be butane and methyl propane. So they would both have the same molecular formula, but they clearly, one of them is a straight chain molecule, the butane is a straight chain molecule, and the methyl propane is a branched molecule. And so we spent a fair amount of time on that, and then we also realised that there was another type of isomerism called stereoisomers, and obviously had the same molecular formula, but also had the same structural formula. So they weren't immediately obvious if you were given a particular condensed structural formula. And the difference between them was that their atoms were actually arranged differently in space. So their spatial arrangement of those atoms was different. And the one we looked at in the AS content was geometric. That was a feature of alkenes, or with alkenes, compounds with a carbon double bond. That carbon double bond was lacked rotation, lacked the ability to rotate. There was no free rotation, which meant that it allowed for the possibility of a different arrangement of atoms in space. And we classified those different arrangements using the notations, the prefixes E and Z. So we could have an E isomer or a Z isomer, and we looked at, it was all about the priority, comparing the positions of the highest priority groups either side of the carbon-carbon double bond. So it isn't automatic. One of the things that we realised, that just because something has a carbon-carbon double bond, it doesn't mean it definitely has geometric isomerism. But if we do see a carbon-carbon double bond, we should be looking and checking whether it has geometric isomerism. Well, today's lesson is focusing on optical isomerism, so the other stereoisomer type of isomerism that we can consider. it has a little description here. Again, just like with geometric, we're going to be talking about molecules with the same structural formula. But in this time, and perhaps this doesn't mean a great deal at the moment, but we're going to be looking at molecules that have no line of symmetry. They are asymmetric, and they are non-superimposable as a result of that. And we'll consider what we mean by non-superimposable a little bit as we go further through the lesson. Okay, so there are various ways that we could sort of begin to explore this topic area. We could go straight for identifying them first, but I've decided to start with their name. The fact is they're called optical isomers, and the optical part of their name is really comes about because of the consequence of the isomerism rather than necessarily an explanation of the isomerism. So one of the things to say, though, is that we are looking at compounds that are going to exist in mirror image forms, or have the potential to exist in mirror image forms. All right, so these mirror images here, that's very, very important. They're called optical, or where the reason the name comes from is because of their effect on plane polarized light. So we're going to look shortly at what we mean by plane polarized light, and we're also going to look at what we mean by the effect. But it comes about because they have an effect on light, and that's why this sort of term optical. And then the other thing we just need to sort of establish before we move on is that given that we are talking about mirror images, then we can focus on the idea or the notion that optical isomers exist in pairs. It is a little bit more complicated than that, but that's how we're going to start. So these isomers exist as pairs, and we have an image at the bottom there, which is giving the idea of mirror images. It's showing a pair of molecules. There are a few things that we still need to explain. It's got the things. It says chiral carbon. We're going to need to explain what that means. And also you'll notice, or hopefully you'll notice, the fact that the particles, for want of a better word, that are attached to each carbon, there are 4 different colours, and that's also going to be a factor. So we're going to understand that diagram a lot better as we go through the next few slides. Okay, so what do we mean by plane polarized light? Well, we're looking at a technique called polarimetry, and if we're going to discover whether a substance can rotate plane polarized light, then we need to use an instrument called a polarimeter, and sort of our little diagram here and what we're going to say is going to help us understand what we still mean by plane polarized light. So light vibrates in all directions, and that's sort of what the image at the beginning is supposed to represent. So you've probably at GCSE, you would have done light or the electromagnetic spectrum at some point, and you would have known it was a transverse wave, and you would have drawn waves. It's terrible, but you would have drawn waves of that nature there. So we have light being emitted at the beginning here. It's sort of vibrating in all directions, but it goes through something called that's a Polaroid. All right, it's a sheet of Polaroid, and you can think of it a little bit like a gate, I guess. So what it does is it only allows light that's vibrating in a particular direction through. And this is how Polaroid glasses work, or Polaroid sunglasses work. So only light in a particular direction, which in this case is a sort of vertical direction, which doesn't really make sense with that gate, but anyway, you just have to live with it. Only that is passed through. So we are ensuring that the light that we're going to pass through our substance is only vibrating in one particular plane, hence the term plane polarized light. So all the waves are vibrating in the same plane now. Now, as we saw earlier, optical isomers are substances that rotate the plane of polarized light. Now, we said that they come in pairs, those optical isomers, and we said that those pairs were called enantiomers. And we find that one of those optical isomers, one of the enantiomers, will rotate that plane of polarized light in one direction, in a clockwise direction, and the other, the second of the pair, will rotate it in an anti-clockwise direction. So we've got at the bottom here, try and sort of show this polarimeter. So we've got our source of light at the beginning, okay, and that is vibrating in all directions, and then it goes through a sheet of Polaroids. So that ensures now that we have light only in one plane, vibrating only in one sort of plane. So here it's just perpendicular. Then we've got our sample. Our sample is in this vessel, for want of a better word. And what we can sort of vaguely see, I think, hopefully in this image, there is that the plane is being rotated. So it's being, in this instance, it's being rotated in an anti-clockwise direction. And so at the end, we can see that from between 4 and then, so from before it goes into, before it comes out, we can see that the plane has rotated, that the light has rotated. We would be able to determine by what extent it's rotated using sort of, it's like an eyepiece at the end, which we could turn until we block the light out, and that would show us how far it rotated, and we'd be able to see how many degrees that the light had been rotated by. So we're not just discovering that it's being rotated clockwise or anti-clockwise. What we actually find is it will be rotated by a specific number of degrees, and that enantiomer would always rotate it by that specific number of degrees. Now, when we make optical isomers in the lab, they're typically made in 50-50 proportions, i.e. we'll get 50% of one of the optical isomers and 50% of the other optical isomer. We'll understand better when we do the next topic, which sort of this leads into, why we get a 50-50 proportion. So we're not going to focus too much on why we get 50-50 at the moment, just the fact that we do. And we call that 50-50 mixture a racemic mixture, okay? So that is like a key term. So understanding, appreciating that racemic mixtures are mixtures of a compound that contain 50-50% proportions of the two optical isomers, or of two optical isomers of that substance. So we said that one enantiomer would rotate in a clockwise direction and one would rotate in an anti-clockwise direction, and we said that they would rotate light by a specific amount. So it would vary for each substance, but it could be 20 degrees, 30 degrees, whatever. Now, because we've got a 50-50 proportion, we've got the same amount rotating in the clockwise as there are rotating in the anti-clockwise direction. What we actually get as a result is that there is no net rotation. So even though we have a mixture of optical isomers, because of the fact that they are the same substance and because of the fact that they are present in the same quantity, we observe no net rotation. So it appears that that optical isomerism isn't present. So there's no net rotation because they cancel out. So we have to be mindful that racemic mixtures have no effect on the plane of polarized light. And that means, in a sense, what we've got to be aware of is that because something doesn't rotate plane polarized light does not automatically mean that it does not contain optical isomers, because it could do if it was a racemic mixture, if it was a mixture of an optical isomer of optical isomers in 50-50 proportions. Okay, so the eagle-eyed of you would have noticed on an earlier slide, I sort of skipped over it, and I shouldn't really have written it actually in hindsight, because this is the point of this slide, is to introduce it, but you would have noticed that you would have seen that word chiral earlier. So one of the things that we stated right at the beginning was that optical isomers are non-superimposable. That means you can't slide one over the other. So a good example of that actually are your hands. If you look at your hands, if you put them in front of you now, you can see they are mirror images of each other, really. You could put a dotted line between them and it would look like one was the reflection of the other. But the point is they're non-superimposable because they do occupy a different spatial arrangement, right? So you could wear a right-handed glove on your right hand, but you couldn't wear a right-handed glove on your left hand. And if you put your hands on top of each other, they're non-superimposable. They are mirror images of each other, okay? So this is what we mean here by this type of stereoisomerism. What that also means is that they have no plane of symmetry. So your hands do not have a plane of symmetry. And we describe something as a molecule as not having a plane of symmetry. We describe it as being chiral, okay? And actually it comes from the Greek word, which I'm probably going to mispronounce, kia, I think it's pronounced anyway, but that's where chiral comes from, and it's the Greek word for handedness. So often, sometimes chiral or optical isomers are described as having handedness, which is possibly a slightly odder way of putting it, but anyway. And that word chiral or chirality, it's all referring to the same thing. It's referring to optical isomerism. And what we can try to identify in a molecule is something called a chiral center, i.e. if we find one of these, we will know for a fact that our molecule will exhibit optical isomerism. And the way we spot whether something has a chiral center or not is that we are looking for 4 different groups attached to it. And if we have 4 different groups, there is no way it can have a line of symmetry. It must be asymmetric. Now, this 4 different groups, the groups bit I want to be slightly vague about, as we'll see in a second. I haven't written 4 different atoms. You might see 4 different atoms maybe somewhere. That's not terribly helpful. And I guess groups isn't perfect either. But we've got to have clearly, what we can't have is the same thing attached to that carbon. The moment we have something attached to a carbon, we have 2 things that are the same, then we can't have a chiral compound. We can't have something that exhibits optical isomerism. And this is just a sort of visual image to sort of emphasize that non-superimposable bit. So we can see, well, hopefully you can see that we've got mirror images. I can sort of draw my my mirror. It's not very good, but anyway, and we can see that if we didn't actually have 2 hands, we were only showing 1 hand, the other here in this diagram would be the mirror image of it. And you can see on this picture, on the example molecules, that we have got 4 different things attached to the carbon. So what would be considered the chiral carbon here would be this here, okay? So this is a chiral center in this example here. And we have got 4 different groups attached. Of course, you can see one of them is an atom. So we're just using groups in a sort of general way. Okay, so how could you spot something like that in an exam, or in an exam question or whatever, or just on any organic molecule? So I want us to look at the top one first. So the top one is probably the easiest to sort of recognize. So what we've got, I've used the colours. The colours are there to show that we've got 4 different groups. So we have got an ethyl group, we've got an OH or a hydroxy group, we've got a methyl group, and we've got a hydrogen. Okay, so we have 4 different groups attached to the carbon. That is going to mean that it will have a chiral center, that carbon is a chiral center, that this molecule will exhibit optical isomerism. Now the one below is very important because sometimes people can spot the presence of a chiral center if they have something like a cyclic ring attached, because to them what they think is they may initially think that they have got only 3 groups attached. So sometimes they think, oh look, I've got one there, I've got one there, and then they may view that as just a 3rd group. So, and that's why group is not perfect here. But what we can see, I hope you can see, is that we do have still 4 bonds, right? So we've got 4 bonds, 1, 2, 3, 4. And then the reason for my colours, the yellow highlighting and the purple highlighting, is if you just go along those bonds, you can see there's a difference that there is a difference. So on the right hand side, on the one that's highlighted yellow, we do have like a double bond there, carbon double bond there, whereas we don't have one on that side. And that's different, and that means we don't get symmetry. So really what we're looking for is we're trying to find a carbon through which there is no plane of symmetry, and the four groups approach is a very useful and helpful way to identify the fact that there's no plane of symmetry. But it's the plane of symmetry that is the crucial thing, or the lack of plane of symmetry. The fact that it's asymmetric is the crucial thing, not the four groups. The four groups is what shows us it lacks symmetry, but it's the lack of that plane of symmetry that matters. Okay, to help you hopefully appreciate that better, what I'm going to draw is I'm going to draw a slightly different version of that second compound, the one at the bottom. I'm going to draw a slightly different version, a version that is not that does not have a chiral center, but actually looks very similar. Okay, so you'll see that I've drawn the same molecule but without that carbon-carbon double bond. I'm just going to show the H just so we can see. But if we were looking for a line of symmetry, we would see that there was a line of symmetry straight through here. And if you're worried about that hydrogen and thinking, hold on a minute, that's not symmetrical, the way to think about this line of symmetry is that this hydrogen is completely behind it, and that the OH is sort of forward. So it would be a plane. There would be a plane that went through the OH, through the H, and then went through the center of that cyclohexane structure there. Okay, so that has a line of symmetry. So it's not chiral, or yeah, not a chiral compound. Okay, so I hope that has helped. But we are going to look at an exam question as an example too. All right, so a little exercise for you, just to try and sort of check your understanding there. So we've got three compounds. At least one of them is chiral. So there will be something to say, there will be at least one of them that's chiral. So I want you to pause the video and then have a think about which of them you feel is chiral, and then we'll look at the answer. Okay, if we look at the first molecule, really, we can rule this out actually straight away, because every carbon in that first molecule has at least two hydrogens attached to it, and if it has two hydrogens attached to it, that means it cannot have four different groups, because already two of them are the same. So we can rule out the first one straight away, because every carbon, there are only three, but every carbon in that propan monol has at least two hydrogens attached to it, so cannot be chiral. What about the second one? Well, if we let's get the spotlight thing. Sorry. So if we look at the first carbon here, we can see that there are three hydrogens attached. So that clearly isn't a chiral center. If we look at this one here, well, what have we got attached to it? So we have got an OH group. We've got a hydrogen. We've got a methyl group, and crucially, because of the fluorine, we have a different group, a fourth group. So around that central carbon here, we have four different groups. So that would be a chiral center, and this molecule here is chiral. So we're going to give that one a tick. What about the one on the right? Okay, so we start from the carbon on the left here. Well, it's got three hydrogens, so that can't be a chiral center. This has two hydrogens, can't be a chiral center. It's got to be a carbon, and that has three hydrogens, so it can't be a chiral center. The other thing, perhaps I should have emphasized a little earlier, is that if you're looking for a chiral center, knowing that you need four groups, the carbon that you're looking at must have single bonds only. Okay, the moment a carbon has a double bond, It cannot be a chiral center because it cannot possibly have 4 different groups. There will be a line of symmetry through it somewhere. And it can be difficult to see chiral centers when you've got rings, which I already mentioned, because you can forget about the hydrogen, or particularly with skeletal formulae, because again you can forget about the hydrogen. So it only, because we draw or show the hydrogen on the carbon that we've got the arrows to here, that is what allows us to see that we have 4 different groups. So let's just try and, so we have got, that would be, you can think of that as another one. Sorry, that wasn't very good, was it? But we can think of, yeah, there's our second. We can think of, it doesn't really matter how far I draw this loop. The point is they are different. You can't draw a line of symmetry through between the blue and the yellow there. So again, there's one. And then finally, basically the rest of this, what this is then attached to. So we have 4 different groups, you see. So we have the 2 enantiomers, we have those 2 optical isomers, and this molecule here is the drug thalidomide, which we'll probably learn about a bit more about it shortly. Okay, so another little exercise for you. So you're going to have to draw these. There's no way that you can decide whether something has a chiral center or not without drawing it. So I want you to draw all of these molecules, pause the video, draw them all out, try and see if you can find any carbons with 4 different groups attached to them, asterisk them. So one of the things to say is that the convention in particularly, well, let's focus on the exams. If they asked you to identify a carbon on an image, you would identify it using an asterisk. If you look online, you'll find molecules where they've identified any chiral centers, as asterisks, with asterisks. So just bear that in mind. So anyway, pause the video, draw those structures, and then we will have a look. Okay, so I've drawn them. You've probably drawn them as display formulae because I have sort of assumed some things because I've an idea of what I should be looking for. So just focus on what you've drawn. If we look at the first one, propan 1-ol, and we focus on the likeliest candidate for a chiral carbon, which is the carbon in the center, because clearly the methyl ones, those carbons would have 3 hydrogens attached. If we focus on that, we can instantly rule it out because we see that we have 2 methyl groups, 2 of the same group attached to that carbon. So that cannot be a chiral carbon. It can't have be a chiral center. Just to confirm that we've got a second and we've got a third group. Okay, so we have got 3 groups, but not 4. What about the next one, but and 2-ol? So we've got an ethyl group, we've got a methyl group, we've got a hydroxy group, and we've got a hydrogen. So yes, we've got a chiral center there. So we would asterisk that. And so yeah, so we've got an optical, something that could exhibit optical isomerism there. What about the 1-iodo 3-methyl pentane? So we have a methyl, we have a hydrogen, we have an ethyl, and we have an iodo-ethyl. So yeah, that's also going to exhibit optical isomerism, and we have a chiral carbon there at the center. When we look at 1-bromobutane, and we look at those carbons that are along the chain, each one of them has 2 hydrogens attached, at least 2 hydrogens attached, sorry. So all of the carbons in that molecule have at least 2 hydrogens attached. So that instantly rules it out. So one thing to look for is find a carbon with only 1 hydrogen, and that at least is a starting point. A carbon that has 4 single bonds, but only one of them is to a hydrogen, and that is a starting point. It doesn't mean it's definitely going to have a chiral center, but it's already, you've sort of jumped the first hurdle, so to speak. What about 3-methylhexane? So we have got an ethyl group, a methyl group, propyl group, and a hydrogen. So yeah, we've got a chiral center there. Okay, asterisk that. And then lastly, we've got this 2-chlorobutane, and we've got a methyl, got an ethyl, got a chlorine, and we've got a hydrogen. So yeah, we also have a chiral center there. So we have 1, 2, 3, 4. So 4 out of those 6 molecules exhibited optical isomerism and have a chiral center. Now, sometimes in exam questions, you have to be able to, or you have to draw, sorry, 2 optical isomers of the same molecule. And you'll notice here that what we've got here is we've got our tetrahedral shape. So this is one of the things when you did shapes of molecules, as I hope you practice drawing a tetrahedral shape. You can probably get away without drawing the dashes and the wedges, although I think really it is good practice and you should try and practice this. It's not difficult. The way to approach drawing a tetrahedral shape like that is just to focus on the central carbon. So if I just do that, so there's my carbon, and then to just practice drawing the 4 bonds. So 2 of them are going to be just straight lines, and then on the same sides you'll have the wedge getting fatter, so that's a perspective where it's coming out towards you, and then you have a dash where it's getting thinner. If you can just practice drawing that, because then all you have to do then is you just write whatever you want at the end of each bond, okay, whatever the groups are. But you need to practice that. You would probably be able to get away in an exam with doing something like that. And so that's fine. You should at least definitely be able to give the impression of a tetrahedral shape like that. But I think it is, again, if you want to go any further in, if you're planning to do a degree which has any form of chemistry involved, so it doesn't have to be a chemistry degree, it could be biochemistry or whatever, I think it's to your benefit now, it's to your advantage to try and practice drawing these tetrahedral shapes. So pick, I'm trying to think now, what do we have that was, chiral was butane, did we have butane 2-ol? So let's assume we did. We would have had, clearly we would have had an OH group, and clearly we would have had a hydrogen, doesn't matter where we place them, and then we must have had a methyl group, and we must have had an ethyl group. Okay, so we can just double check that is butane 2-ol. So first carbon, second carbon, so that's the second carbon the hydroxy or the alcohol group's on. 3, 4, so it is but. So anyway, okay, so you can practice drawing that, and if we were drawing the mirror image on the other side, clearly the hydrogen has to go furthest away. We're going to have the OH. You don't have to draw it so that it's the H and then the O. You could have still drawn O and then H, if that makes sense, but you've got to make sure that the bond from the carbon is to the oxygen. And then we have got our methyl group, and we have got our ethyl group. Okay, so you could have drawn something like that. But practice it, right? Really. So go back, look at the ones that we identified as having chiral centers, and try and draw the 3D shapes of those, please. We will come back, or you will come back, to do chirality and stereoisomerism when you look at transition metals towards the end of year 13. So this is not really for now, this is not really for the organic part of the course, but it is just to highlight that once we move on, whilst chirality could always feature in any aspect of organic chemistry, and in fact it will definitely feature again, if not least in the amino acids section, it can also be a feature of inorganic chemistry. So these will make more sense once you get to the end of the course, but basically these are complex ions. So we've got a transition metal, we've got iron at the center of a complex, and we've got 3 different molecules that are coordinated to it. This terminology will make more sense, and it is possible, as you can see with the two images at the bottom, that to have a mirror image. So it is possible to have optical isomerism in things that are not necessarily carbon based. And again, here's another example. Again, it's a complex ion. Again, you'll see it's got a transition metal at the center. Okay, all right. Okay, so we're just going to take a look at an example exam question. I really like this question. It's not a type that necessarily comes up that often, and that's probably what makes it trickier, because people will do this at some point, probably not get it completely right, and then forget about it because something like this doesn't appear again. But you have to be ready for questions like this. So they're telling us that we've got 3 pairs of isomers, okay? They all have the same molecular formula. They all have that, they're all C6H12. It tells us that P represent a pair of optical isomers, so that's the chirality we've just been looking at, so that's what we're going to do first. Q can represent a pair of geometrical isomers, and R can represent another pair of geometrical isomers, but which are different from Q. Other important bits of information which people will miss, and if you miss this and you don't follow this, you will automatically get it wrong, because they will have to be wrong. They are branch chains. Okay, so every molecule that we draw now to try and represent P, Q, and R must have a branching somewhere. And then the other key thing is that none of them are cyclic. So all of these, this does follow the general formula CnH2n, which is the general formula for alkenes, although we also know that that's also a general formula for cycloalkanes. But we've told that none of them are cyclic, so we won't have any cycloalkanes. So we will definitely have carbon-carbon double bond present in every one of our examples, including our optical isomers. Okay, so let's start with P. So we only need to draw initially something that we know has a chiral carbon, and that satisfies that molecular formula C6H12. And we know that whatever we draw has got to have a carbon with 4 different groups. So let's draw our carbon, and then let's draw 4 bonds. Okay, so how do we proceed next? Well, look, always just give one of them a hydrogen. Almost certainly at A level, we can make that assumption that one of them is going to have a hydrogen attached. And then the next thing to add, which just is very likely to be the case, and you're always going to check it at the end, is that after you've drawn a hydrogen, draw a methyl group. Okay, and almost certainly, whenever you're having to come up with an optical isomer like this, it's going to have a functional group. So we've got to accommodate the functional group. Now, if this had been an alcohol, the next thing I would have added was an OH group, because almost certainly the chiral carbon would be the carbon attached to the OH group. If it had been a haloalkane, I would have put the halogen there. Almost certainly, not definitely, but that's like a good starting point. What we do know in this one, though, is that they definitely have a carbon-carbon double bond. So I'm going to draw, add a group in which I've got the shortest, because I've only got 6 carbons and I've used 2 already. I mean, the shortest sort of group I can attach that has a carbon-carbon double bond. So I'm going to have CH2. And then that means I've used up, then let's think about what I've done. I've used up 4 carbons, so I've got 2 left. And I have used up 4, 5, 7 hydrogens, so I have 5 left. So I have 2 carbons, 5 hydrogens left, and that is quite simply a an ethyl group. Apologies for that. And then the thing to do is to then, once you think you might have it, is to check it. So I have 1 group, second, third, a fourth. It's not asking me to draw the sort of mirror image of the 2 isomers here, because if you look at what it actually says at the bottom part of the question, it says draw 1 possible structure for one of the isomers of each of P, Q, and R. So that is definitely 1 for P. However, just to help you, because we're not just answering this question, we're trying to use it to learn more about chiral compounds or optical isomers. If I was to draw it, the thing would be to do first would be to draw my two tetrahedral shapes, which I've done there, and then to just add the groups that I wish, but making sure that the same group is attached to the same type of bond. Oh, sorry, not type of bond, but you know, whether it's the wedge getting fatter or the wedge getting thinner or whatever. So let's just put the hydrogen here, hydrogen there. Let's put the methyl group there and the methyl group there. Sorry, it's a bit small and messy. Let's put let's do it sort of similar to the way I've done it there. So CH2, CH3, CH3, CH2. Oops, actually, that's not very good. I should have that carbon attached to the bond. Let's just do that again. Okay, so H3C, H2C, that's not very good. Anyway, and then we can have our CH2, CH, and CH, CH2. Anyway, so, and if we'd had to do that to show a mirror image, that's what we could have done, something like that. I could have just written this one at the top, incidentally. Let's just show you. I could have written that as CH3, CH2. I don't need to make it look literally like a mirror image. I just need to make sure that the groups are sort of in the right places in the mirror, sort of reflecting each other in the mirror. Anyway, I hope that part of it was helpful. Okay, so we've got Q can represent a pair of geometrical isomers. All right, so one of the things that we've got to remember is they're branched. So let's have a look. So we're going to do Q next. All right. Okay, so the first thing to do is to draw the carbon-carbon double bond, because we know that is the key feature or the principal reason or the cause or whatever of geometrical isomerism. And I think it helps to draw our sort of trigonal planar, if we're looking down from above, shape with the remaining bonds that would be attached to those two carbons. And similarly with P, I would start with one of the carbons having a methyl group and a hydrogen, because you know we've only got 6 carbons, so we don't want to just waste them. So always try and keep things initially as sort of simple as possible. So when we look at the right-hand side, we've got now 3 carbons left, and we have got 8 hydrogens. Now, if we just write a hydrogen and then when we have 3 carbons in a line, we're not going to get the branching that we're supposed to have. So a way to get branching is to have a methyl group, and then we've still got 2 carbons left. So we're going to have different priority groups. So we're okay there, is to do then the remaining carbons and hydrogens. So if we count those carbons, we've got 6. If we count the hydrogens, we've got 12. If we want to just double check, we've got geometric isomerism. If we look at the left-hand carbon, we compare the methyl and the hydrogen. The methyl group is the group with the highest priority. If we look at the right-hand carbon, we've got a difference in priority between methyl and ethyl. So the ethyl is the highest priority. Something else is that we've got to have a branch chain molecule. So first of all, let's establish our longest chain. Okay, so there's our longest chain, and we do in fact have a branch of it. We have a methyl group attached. So we've ticked all the boxes there. So we've got one of the pair of geometric isomers, and all we would need to do to draw the other is to swap. Well, we've got an E isomer here because we've got the highest priority groups on opposite sides. We would just need to, with one of those sides, is to swap the 2 groups so that we ended up with the 2 highest priority groups on the same side. So we had a Z isomer. Okay. Trickier though now, once we've done that, is to come up with an alternative set of geometrical isomers. So we've got to do R. So we're still going to start in the same way. So, you know, just basically get everything ready for yourself and don't try and think it all completely in one go. Take it step by step. Now we still don't have any more. We don't have any more carbons than we got before. We have no more hydrogens than we got before. So I'm going to try starting with, on one side, the same as we did before, the methyl and the hydrogen. Now we've only got 3 carbons left. We've only got 8 hydrogens left. I've got to have branching, but the moment I write a methyl group on the right-hand carbon, I'm just going to be drawing a version of Q again. So I have to think, is there any other way I can do branching? Well, there is, and I'm going to draw it not in the way you would, but to show so it's clear about the branching, is I can have branching on the final group that I add to my molecule. So I can have 2 methyl groups attached like that, you see. So I would represent that, just to be clear. I would represent that. I would write that as CH3 2. Okay, that's what we've got here. Okay. Now I've got my 6 carbons. I've got my 12 hydrogens. Have I got my priority groups? Well, obviously on the left hand side it's the same as before, and on the right hand side again I've drawn any isomer, and I do have a difference in priority groups, so I do have my geometric isomerism. If I look at whether there's branching, well, let's find the longest chain, and yes, I do have branching. I think that's tricky. You have to be aware and prepared for the branching to not necessarily be where the carbon-carbon double bond is, for it to be somewhere else off the longest chain. Okay. So we're going to consider now the chemical consequence of chirality. It's not a huge feature really of the A level. I can't really remember any questions about it, but it is important, and I think if you're, in terms of thinking about the future, or thinking about what degree you might do, the chirality could feature quite heavily, particularly if it was a biological science or biochemistry or something. Would be a significant feature, I think. So chiral compounds, that chirality or optical isomerism can have a consequence when it comes to chemical reactions, and the reason that can happen is because of basically this idea of things fitting or not fitting. So we talked about early on about chiral compounds being non-superimposable, and we gave the example of trying to put a left-hand glove on a right hand, and basically it's not the correct shape. And if you think about other areas of science that you've done where shape has mattered, I think at GCSE you will have done enzymes, and you will have done the idea of them having an active site, and this active site having a particular shape, and that shape fit a particular different molecule, so enzymes performed specific roles or jobs. The other aspect of that you did was that if the conditions changed significantly, whether the pH or the temperature changed, the shape of that active site could change, and in so doing could either reduce the effectiveness of the enzyme or just stop it completely. So you had this idea of denaturing, or a denatured enzyme which no longer worked, and basically because the shape of the active site it changed. It was like you called it a lock and key method. And that's a little bit another way of thinking about chirality, maybe, is thinking about a lock and key. So you could have 2 keys that are absolutely identical to each other, except they are mirror images, and only one of them would fit your front door lock and the other would not. So so that's how a consequence of chirality can feature, particularly in nature. So many natural molecules, in fact, are chiral. this is just a sort of an example where we can see the fact that molecules are chiral in nature. So we've got an edible snail here, or two edible snails, and if we were to look at 20,000 of edible snails, we'd find that all but one of them had the spiral of their shell on the right hand side. So clearly the building blocks of that shell have had a particular shape, but the fact that our other one could have our anomaly due to a genetic mutation could have its shell on the other side, on the left hand side, meant that clearly something somewhere had meant that the building blocks were built in the opposite isomer, as it were. The other optical isomer was made instead of the one that was typically made for the other 19,999, and so we got the shell building so that the spiral was on the left hand side. That's not really an important or significant consequence, but it is a visible one. You did amino acids, certainly at GCSE, so the idea that proteins were made up of amino acids. Well, it turns out that all of those amino acids, except for glycine, are chiral. So they will all, there is actually the potential for two optical isomer versions of those amino acids, but in fact only one of them will ever occur naturally. That is with the exception of glycine, and the reason glycine is an exception is because it doesn't actually have a chiral carbon. That's because the carbon that would be chiral has two hydrogens attached. Glycine is the simplest amino acid. So in nature, where there could be a number of optical isomers, typically only one occurs. Many drugs are optically active, so there might be more than one enantiomer, and only one of those would have a beneficial effect. And it doesn't necessarily follow that the other is just benign. It could actually have a harmful effect. So thalidomide is an example that we're going to just briefly look at in a second. So optical isomerism is actually incredibly important in nature. So we did look at this structure actually when we were looking at identifying chiral centers earlier. So this is thalidomide. So in chemistry, you get this S and R notation. If I'm happy to explain that to you, but not in this video. In biology, what you tend to see is a plus and minus. They sort of as a notation, but in chemistry it's S and R. So it's the S version of the thalidomide, which is the effective drug, and the R1 actually is the dangerous one, which caused harm. And one of the problems is that even if you only administered the effective version, some of it, or I can't actually remember if it's some or all of it, but some of it will convert to the dangerous version. So the body itself was sort of increasing the risk of harm. So I think it was a drug actually. It says here in the 60s, but I think it was actually really administered in the late 50s, and the sort of effects were really understood at the beginning of the 60s. The consequences, the damage. So thalidomide was prescribed for a variety of different conditions, but the one that in particular that is relevant here was it was an anti-nausea drug, and so it was given to some pregnant women to help reduce the effects of morning sickness. And if they took it between in a particular time period of their of the gestation of the fetus, then it could lead to a whole different range of fetal development issues. So it could be that it affected limbs or the development of internal organs or the brain or eyesight or hearing. So there were the very significant and serious consequences to the drug, taking that drug. So then once these effects were discovered, and it did take some time, in part because it was known, the drug was known in, had different names around the world. So it wasn't always easy to tie it all into one thing. It got banned, but it has actually been started to be used again to treat leprosy and HIV. And naturally, or of course, female patients will have to have a pregnancy test and use 2 forms of contraception if sexually active if they're prescribed that drug. Another example of optical isomerism that has, or here's an example with a 2 different physiological effects, is that the molecule that's principally the cause of the smell of caraway seeds and the molecule that's principally the cause of the smell of spearmint, they are optical isomers of each other. So the molecule is carvone, and we have the S version and the R version. Similarly with lemons and oranges, we can see optical isomerism in the molecule that's responsible for their respective smells. And an even more dramatic difference in their effects is if we look at S-methamphetamine, that's an illegal psychotic drug, and R-methamphetamine is a nasal decongestant. So that seems an appropriate point to finish our lesson on optical isomerism, and if you have any queries, let me know. Thank you.